Alright, here we are, day number 3 of alternating series and more tests, chapter number 7. Today we're going to talk about partial sums and error. So before we spoke about the integral test, and we said that if something looked like we could integrate it, we could use the integral test, and if that integral came out to be a finite number, countable number, like this one actually comes out to be 1. That just tells us, hey, we get a finite number. That means it's convergent. And actually, this number right here, this 1, is not the sum of this series, but it's actually pretty close. So we're going to actually use partial sums to find error. So let's say we took that same series here, but we only took it up to the 5th term. We could actually use this integral and the value that we'd get in order to come up with an approximation, right? An error. So this would be an approximation. We get a number, right? Plus, so this would be the sum of those first 5 terms approximately, plus then the extra, and that extra we're going to call the remainder. We're going to call the remainder of the 5th partial sum. And that remainder is going to have a special property related to integrals. So let's get started. On the next few pages of your notes, you'll see Convergence series test practice. This is just some really good practice you can use with all of the tests we've gotten so far, including ratio test, integral test, writing things as partial fractions, what else? Comparison test, limit comparison test, and all that good stuff. Okay, so how does the series converge if the integral converges? Alright, this is just talking about what we just looked at, right? Let's consider this situation right here, just the representation of some series, right? So this first rectangle would be a sub 1. The second rectangle would represent a sub 2, etc. on down the line for an infinite number of terms, right? If we're looking for that infinite sum would just be the sum of all of those pieces. Okay, so the integral in this way is a pretty good estimation. Okay, it's a pretty good estimation, but it's not perfect, right? Because of these little gaps in here. All these little gaps then add up, and we've got some error. Okay, so as we go to the next page here, I want to look at the relationship between the integral and the partial sum. Okay, so the partial sum, let's say this yellow space here is S4, right? It's the sum of the first 4 terms. Well, if I were to highlight the remaining in yellow, which I'm about to erase, okay, that would be the remainder, right? What's left over, or how far off from the actual sum we are. So let me erase that, and now I want to do a representation of that. This purple line that you see here, this represents the integral of that series, that sequence turned into a function. Right, so that is the representation of the integral. Now if I zoom in on the portion that represents the error, the portion of the integral that starts here and goes here would be related to the error. Okay, here's the error. That integral from 4 right here to infinity of whatever the function would be is going to be an overestimate of that error. Okay, now I'm going to take this and hopefully give you a good visual of what I'm talking about here. But an underestimate of that error, so we can kind of trap that, is going to be the integral from 5 to infinity of that function dn. Let me show you the representation there. Okay, so here's a5. That's going to be an underestimate, and the question why comes up often. Okay, so wouldn't that be the fifth term? Well, if I shifted that over, notice how that is always going to be greater than that blue integral. Therefore, what that means is that our error will always be greater than the integral from the next term on. Okay, so now we have a way to trap that error. Okay, so notice originally we said the partial sum of the first 4 terms plus the error, well, that would have to be somewhat close to or equal to the infinite sum. Okay, so if I can target this error, then I can come up with a potential sum for the infinite series. All right, let's try an example. Okay, so suppose we can use the integral test to show that the infinite sum of that sequence is convergent. Show that the error r sub k is in approximating that infinite sum by adding up all those terms satisfies that. Well, we just did that on the last page. Let's determine the number of terms necessary to approximate that, the infinite sum, right? Correct to 2 decimal places. I want to do one quick thing. This shouldn't be 0.01, it should be 0.005. That's the definition of 2 decimal places right there. Okay, so what is that asking me to do? That's asking me to take the integral from some value k to infinity of the function notation of that sequence buried in that series. Okay, so let's go and tell me the number of terms I got to go out in order to get an error of that. Okay, so let's do a little integration. So if I integrate n to the negative third, that would be negative n to the negative 2 over 2, evaluated from k to infinity. And I want it to equal 0.005, which, in case you didn't know, is 1 over 200. So I want to find an error. I want to find out how many terms I got to go out in order to get an error of 1 over 200, or to be that accurate. Okay, so let's plug those upper and lower limits in. Let's take the limit as b goes to infinity. Remember, we're improper integral here. And I'm going to rewrite this, negative 1 over 2n squared from k to b. Did you ever think you'd be only dealing with letters in math? Well, now it's a reality. Okay, so the limit as b goes to infinity of negative 1 over 2b squared, which, by the way, when b goes to infinity will go to 0, minus negative 1 over 2k squared. Okay, so this first term will go to 0, and therefore we get minus a negative will make this 1 over 2k squared. And we want that to equal 1 over 200. Okay, so how many terms we got to go out? You might already be seeing it. So 2k squared then has to equal 200. So k squared equals 100. So it looks like we got to go out 10 terms. 10 terms. And I would say greater than or equal to 10 terms, right? Because your error, you want to err on the side of a larger error. So I would go greater than or equal to 10 terms just to kind of catch all and ensure that you meet that standard or better. Okay. Here is actually that example, that same example here in part B. Part A is just basically the graphical representation that we already talked about, finding the error, so we should be pretty good there. So let's go ahead and do a little bit of work here. Okay, for purposes of time and not being able to show you how the calculator would work, part A we'll just do in class, where we can use our calculator to find the sum of the first 10 terms of this. But basically the first term would be 4/5, the second term would be 4/8, the third term, and so on, right? So if we want to estimate the error, right, we could say that the error of this series, or the remainder of this series, would be between the integral from 11 to infinity of all that stuff, right? The error of the first 10 terms, of the sum of the first 10 terms, would be between that and be between this. Right, so we could calculate that. I'm gonna do, let's just do the upper limit of that. Let's go from 10 to infinity and just give it an overestimate of the error. So if I did from 10 to infinity of this thing, I'm gonna pull out the 4, put this in as 1 over n squared. I'm gonna write this in a form that might look more familiar. Plus 2 squared dn. That looks like an arctangent to me, and it actually comes out to be 4 times, remember, this is a, 1 over a, arctangent of n over a. Okay, and we'll evaluate that from 10 to infinity. So let's see what that comes out to be. All right, that would be 2, actually the limit as b goes to infinity of 2 arctan of b over 2 minus 2 arctan of 5. Alright, so it looks like this right here will go to pi over 2. Right, as arctan goes to infinity, that'll go to pi over 2. So this 2 times pi over 2, those 2's will cancel. So I'll get pi minus 2 arctan of 5. Which comes out to be, as a decimal, comes out to be 0.394. Okay, so the error will be less than that, which isn't very good. That's a pretty large error, right? If I were to do the other side of things and take the integral from 11 to infinity of said thing, basically I'd come out with the same situation at the end, except this would be 5.5. Alright, because it'd be 11 over 2 instead of 10 over 2. And that comes out to be 0.359. So I know my error is somewhere in there. Alright, I know my error is somewhere in there. So if I did, let's say I did find the sum of the first 10 terms, and I added, my error, which is somewhere in there, I would have a decent approximation, a decent one, of the infinite sum. Wouldn't be great, but it'd be decent. Alright, so let's look at this. Let's find this to within 0.04. We're going to have to go out pretty dang far, because we went out 10 terms, right, and got an error of this. So that means we're going to have to go pretty far. So I could just take kind of this template of what I've gotten down here, hit this piece, and instead of inputting instead of inputting 10, I'm going to input an n. So I'd have the limit as b goes to infinity of 2 arctan of b over 2. Right, we know this is going to end up being pi minus 2 arctan of n over 2. And I want that thing to come out to be 0.04, I think it was. Okay, so that means that I want, recall that this came out to be pi minus 2 arctan of n over 2. I want that to come out to be 0.04. Okay, so I got a little bit of manipulation to do. I would subtract pi and divide by -2. So arctan of n over 2 would equal 0.04 minus pi over -2. Okay, and then the tangent of that would equal n over 2. 0.04 minus pi over 2. Okay, so multiply that by 2 and we'd have n, approximately. Right? So 2 times the tangents of 0.04 minus pi over 2, oops, over -2, sorry. Yep, -2. That should get us our n value. Let's see what we get using the calculator. Holy cow, you got to go out 99.98 terms, or 8 terms. So I would say you got to go out to n equals 100. You got to go out to 100 terms in order to get an error that small. That's pretty crazy. That's quite a few terms out. All right, so that, I believe, is it for today. That'll be partial sums and error on infinite sums using integrals. Have a great day. We'll see you next time.